How are
Hey,
you, everybody?
Good.
Very good.
we're surviving, sir.
Yeah, I hope everybody's like safe and taking care of yourself, okay? And hopefully the future will be better, you know. So let's see, regarding the lab, what I'm thinking about, I might visit the university next week, and I'd like to find out the possibility if we can able to use the Elvis remotely. I'm not sure. I just read online there is something can be done. So if we'll be able to be there to do that, as will be great. At least we can use like a simulation mode. You can access if you have remote access to the lab, so we can do the experiment at least in simulation mode. So you can see like the Elvis, and then you can do all of your connection in simulation mode. I'll generate all of your results. Okay. So I'm gonna find out. I would say next week. So I'm not sure if it's gonna work or not, but we'll find out if this is gonna be the case or not. Okay. So hopefully we'll work out. Next week I'll visit the university and find out the possibility if we're able to do the labs using the hardware in the university remotely. I'm not talking about hardware. We can use like a real Elvis. We're gonna use like the soft panel of the Elvis, and we can do all of your connection and you can do all of your measurements. Okay. Hopefully this will work out. We need to find out. Uh, Meanwhile, I also request from the university to give us like remote access to LabVIEW and MATLAB. I think they're working on it, and hopefully we'll get back from them very soon. So if this is going to happen, so then you don't need to worry about having the MATLAB and LabVIEW software. So you can access remotely the LabVIEW and MATLAB from the university. Okay. So meanwhile, we're going to do the lab using mainly LabVIEW. Assuming everybody has a LabVIEW. Who has a LabVIEW? Who does not have a LabVIEW? Would you please write in the comment?
I have um I have Charlie's old laptop which has it, but we're still trying to see if we can even turn it on.
Mm-hmm. Okay. So
Hey, Dr. Sam, this is Chris Valley. How are you, sir?
good. How are you? Yes.
I'm doing well. Sam was having an issue with the serial code that you gave us last semester, and it wasn't working, apparently.
Okay.
So I don't know if we need to get with National Instruments on that, or what you did to get
No,
that.
we don't need. I think it should work for 1 year. Should not have any problem. But I will communicate with the National Instrument today and find out what's the reason why it's not working. Okay. But make sure that you are using the right code. I'm not sure anybody like tried recently to download to install the LabVIEW and having the same problem. Okay. So yours work. Would you please write the code here, the activation code here, if yours is working?
I just checked one more time if it works, and as I was opening, it shows some account information and said my name and Texas A&M University Commerce and the code, but it appears only for like I probably can access that information somewhere else. Let me see.
So then good. Would you please just try? Yeah, you will see when you open the LabVIEW, the codes will be there. Would you please just type the code here so everybody can have it?
Yes, sir. I'm sure. I'm pretty sure Chris has it.
Yeah. So this is the code. So please try and let me know if you can download it or not. If not, just email me. Mm-hmm.
Okay, Dr. Tam, I would also like to say this. Dr. Graham actually told me that I can still go to work during this lockdown. So if I can be of any assistance to you or any of the students, just let me know. I emailed her and asked if the students are allowed to come in the lab in smaller groups and if there is any way to do that. So haven't got a response yet, but I'll keep you guys updated.
Yeah. So Yeah, that will be great. I might stop by the university. Are you working tomorrow or not? You're working tomorrow.
Yes, I'll work tomorrow.
So I will stop tomorrow, and hopefully you'll be in the lab so we can find out the possibility if we're able to do remote access for the Elbus there. I think there is an option there that you can work in Elbus either using the PC mode as well as like the hardware mode. I think this is going to work. We'll find out tomorrow, and then if this work will be great. So we'll do our lab using the Elbus there. Okay?
Yes, sir.
Yeah.
I got a question.
Okay. Yes.
That phone number you gave to all of us students, are you able to receive text and calls or only calls only?
What do you mean here?
You know that phone number you gave us 2 days ago.
I'm not sure. I gave you what?
The phone number you gave us 2 days ago.
Yes. Yeah. You can even call me. Yeah, that's okay. That's okay.
Call and text.
Yeah, call and text. That's fine. Yeah, okay. Anytime.
Just want to be sure.
Yeah, anytime. Well, thank you so much. Okay, so let's continue. We start working last time in amplitude modulation, and then what we did mainly was something called double-side band full carrier. What do we mean by double-side band full carrier? I'm sending the message as well as I'm sending the carrier, and mathematically that's how it's going to be looks like. Okay, M is my modulation index, right? Which is mainly dependent on the amplitude of the message as well as the amplitude of the carrier. Okay. Omega C is what? The frequency of the carrier. And omega M is the angular frequency of the message. Okay. So if we multiply VC cosine omega CFT times 1, so we'll get what? We'll get the carrier only. And the second term will be what? Will be MA VC cosine omega C of t cosine omega M of t times cosine omega C of t. Okay. So if we take the Fourier transform for Vm of t, we're going to expect having 3 peaks, one at 1 omega C and 1 peak at what? At omega C plus omega M and omega C minus omega M. So we need to look at the spectrum in this case. So we're going to expect what? Assume this is like V AM omega, right? And here we have an omega. So we're going to expect a peak at what? At omega C due to the carrier. And we're going to expect upper side band will be at omega C plus omega M. And lower side band at omega C minus omega M. And we find out that the bandwidth is required to send an AM signal is mainly 2 omega M in this case, which is will not require too much bandwidth in order to send AM signal. This is one of the advantages of AM modulation. Okay. And what I need from you for the lab to implement this formula using LabVIEW. So by using LabVIEW, you can implement the AM modulation. So implement the signal in time domain, and then as well as in the frequency domain. So using this mathematical formula, you can implement the AM modulation using, I would say, LabVIEW. Yes, Taylor's asking question. Okay, it's asking me if we don't have a LabVIEW, so yeah, it's not necessary to do it today. We'll just go through that, and then maybe you can do it at a later time, okay? So hopefully
there's people
yes.
in teams, right? So if we had the ability to work in teams, then we just make sure one person on the team has LabVIEW.
That's okay. If you can work in a team and then communicate between each other, this is fine. Yeah, it's fine with me, you know. But make sure that everybody contributed to the work on the, you know, on the whatever in the lab. Okay. But yeah, that's fine. If some student does not have a LabVIEW, yes, you can share. And let's see. I hope so. We will be able to do like remotely. Okay. And we'll work on that tomorrow and we'll update you. Okay. So again, what is the condition of modulation index? Anybody tell me what modulation index should be? Modulation index should be what? Should be less than 1. to avoid overmodulation. Okay, and we have done that, last time in the lab, and we found out that the signal will be clipping if the modulation index will be greater than 1. And how we can calculate the modulation index? We have 2 formulas to do that. M is equal to the amplitude of the message divided by the amplitude of what? Of the carrier. And we need the modulation index to be less than 1. Okay, this should be less than 1, right? And we can find the percentage of modulation as well. We just multiply by 100%. So we need the modulation percentage to be less than 100% in order to have to avoid having overmodulation. Another formula we can find out for modulation index is using graphically. We can find out the modulation index by finding Vmax and Vminimum. Vmax is equal EC plus M, which is the highest amplitude in the envelope, and EC minus M is V minimum. And if you remember, if we go back a little bit, so this is mainly the envelope. So this, the maximum value here is going to be what? EC plus EM. And the minimum value we can get here, EC minus EM. So if you increase EM, what's going to happen here? That's is going to go to the negative side. So clipping is going to happen to the signal, and you will not anymore having the shape of what? The shape of the envelope, which is give you exactly like the signal. So one way, to avoid that is making the modulation percentage is less than 100%. Okay, so then again, this again up exactly to this formula, AM over AC. So now the question might raise here, and maybe you can try this one also in LabVIEW. If the input message is a combination of more than one sinusoidal component. So we're having V1 sine 2 by F1 of t plus V2 sine 2 by F2 of t. Like for example, assume having modulation system. Normally, we do what? We multiply the message M1 of t, right? M1 of t times what? Times the cosine, for example, omega c of t. Here we're having one message. What about if I'm having two messages? M1 of t plus M2 of t. Okay? So we need to multiply these two signals by what? By cosine omega c of t. So now the modulating signal is what? Is a combination of two signals with different frequencies. Assuming M1 of t has a frequency of omega 1, angular frequency, and omega 2 has a frequency of omega 2, etc. So then what we're going to expect the output will be here. Anybody? What are you going to expect the output here?
Would you just distribute the cosine omega ct to the W1 and W2?
Yes. So we're going to have M1 of t cosine omega c of t, right? Plus M2 of t cosine omega c of t, right? And if we need to take the Fourier transform for this one here, what we will have? We're going to have 1/2 M1 omega minus omega c, right? Plus 1/2 omega 1, right? M1 omega 1 plus omega c, right? Here we're not talking about the DC value. Plus 1/2 M2 omega 2 minus omega c plus 1/2 M2 omega 2 plus omega c. So we're expecting here 4 peaks, one for omega 1 and one for what? For omega 2. We don't have the carrier here because we are not considering here the DC value. Is it clear?
I have a question.
Yes.
The way this slide comes up, it says it's modulation of a complex signal. Is that's not saying complex like A plus BI with imaginary numbers, right?
No, we're not talking about complex signal like a complex, real and imaginary. No. Here we're talking about like more than one sinusoidal. Okay?
Okay.
Like have different sinusoidal with different frequency and different amplitude. Okay?
Okay. So complex, like complicated, right?
Yes, it's not
Okay,
a complex,
not
like
imaginary.
a complex signal. Yeah, not imaginary and real. Yeah, that's true. Okay. So this is mainly what we're going to expect on the spectrum. So the spectrum, rather having like only 2 peaks as a normal, when we're talking about the carrier, we will expect here to having 4 peaks. So if I need to sketch the spectrum here, we're going to have what? We're going to have like 4 peaks, right? Right? The band is going to have what? At omega 2 plus omega c, and omega 1 plus omega c, depending which one is bigger, right? And we're gonna have what? Omega 1, let's see, this is positive, so this is gonna be the other side, right? This is omega 1 minus omega c.
Dr. Sam.
Yes.
We can't see the whole thing, sorry.
Now you can, now we're okay?
Seeing the whole, what you're writing there.
Now you can see it?
Yeah.
A little bit better. Pull it down to your bottom left.
Okay, and then omega 2 minus omega c. Now it's good?
Perfect.
Yeah, okay. Yeah. So we're going to expect here 4 peaks. Maybe ask me a question why we're not expecting here like 5 peaks. Why is that? Because we're not considering here what? We're not considering the DC value. We just multiply the message with what? With the carrier. Okay? So now the questions here, how we can calculate the modulation index in this case. To calculate the modulation index in this case, which is I'm going to ask you as a homework to find out, M is going to be like a square root of what? M1 squared plus M2 squared plus M3 squared, etc. So this is how we can find the modulation index in this case. Okay? So modulation index will be square root of M1 squared plus M2 squared plus M3 squared. For example, assume that M1 of t is equal 5 cosine omega 1 of t, okay? And M2 of t, take this one out. M2 of t equal 7 cosine omega 2 of t, okay? And the carrier, let's see, V of t is equal 10 cosine omega c of t. And we need to find out what is the modulation index in this case. The modulation index in this case is equal what? M is equal square root of what? M1 squared plus M2 squared. Why? Because we're having only 2 messages, M1 and M2. Okay. Next step, we need to find out M1. M1 is equal what? E1 over EC, right? Which is going to be what? 5 over 10, which is going to be 0.5. Okay. Same thing, M2 is equal what? E2 over EC, which is going to be equal 7 over 10, which is going to be 0.7. So we find out what is M1, what is M2. So then to find the overall modulation index, M is equal square root of what? 0.5 squared plus 0.7 squared. Okay? Which is going to be square root of what? This is 0.25 plus what? 0.49, which is going to be square root of what? 2 is going to be 60, 74.74. It's clear? It's clear? So that's how we calculate the modulation index. Is it clear to everybody?
Can you go back so I can see the original message?
Yeah,
sorry, I didn't get the
original. This is the original message, okay?
Okay, sorry, I just didn't get the numbers.
Okay, which is a combination of 2 messages. I think you can implement this one also, the lab view. You can consider 2 messages, okay? And you add them together and you multiply with what? You multiply with the carrier. And then you can study the frequency domain, which is the beat, what we show here. And so as well as if you look at the time domain, you can calculate the modulation index from the simulation. Look at the envelope, and from the envelope, try to find out, compare this one with, calculate the modulation index theoretically in this way, and calculate the modulation index using this formula from the graph. You're gonna get an envelope, something like that, right? So from the envelope, you're gonna find what is the maximum amplitude and what is the minimum amplitude. Okay, but this envelope here will be a combination of more than 2 messages with a carrier. Okay, so we're gonna expect here at least 4 frequency, right? We're gonna expect 4 frequency if we're not considering sending the carrier. So then after you generate that, find out the amplitude here and find out the minimum amplitude and try to find the modulation index. And compare that with the modulation index that you can get from the calculation. Okay? Is it clear? What do you want to do? Is it clear for the second part? First, you're going to consider one single
Yes.
single message multiply with the carrier, and then study the frequency domain, the time domain, and find out the modulation index as well. Okay. The second part, you're going to do a combination. Yes.
So this is assuming you knew what the original message was, not you're looking at the picture of the modulated system.
Yeah, you know what is your message, and you know what as well as what is your carrier. So you can, for example,
Okay.
you said the message, the amplitude is 5, the frequency, for example, 50 kilohertz. Okay. Message 2 is like 7 volt and the frequency 100K. Okay. VT is the amplitude is 10 volt, for example, and the carrier 500 kilohertz. Okay. And then you're going to generate the envelope. So you're going to have the envelope similar to the one here. And then you can find out what? You can find out what's this peak value and what is the small peak here. And from these two, you can find out what is the modulation index. And theoretically, also, you can find the modulation index. I know what is M1, the amplitude 5, and amplitude 7, and we can follow the same procedure here. M square root of M1 square plus M2 square. Then we can find out M1, we can find M2, and then following the same procedure, we can find out M is equal 0.74. So we need to compare this one here from the envelope. We go to the envelope, right? This is what we're going to generate, right? And this is going to be my maximum voltage, which is EC plus EM. This value will be what? EC minus EM. And then we can find the modulation index from these two values, okay? And we compare it to the square root of 0.74 and find out either it's close or it's not, okay? You just need to verify this formula, if this formula is true or not. Is it clear? Is it clear to everybody?
Yeah.
Yes.
Yes.
Okay, good.
Clear.
Very good. So here we're not considering the, try to do it with what? With the DC value and without DC value. If you need to do it with DC value, that's mean here it's going to have what? You're going to multiply the carrier with 1 plus, maybe it's better to start from here if you need to use a DC value. You're going to do VC cosine omega t plus VM t cosine omega C of t, most likely. Okay? So then here VM of t is going to be like one time is going to be VM1 of t, and the second time will be VM of t. So you're going to start, this is what I'm talking about. So the AM of t is going to be what? The AM of t is going to be what? VC cosine omega C of t, which is the carrier, right? Plus VM, which is the first message. Let's see, M1, right? Multiply by cosine omega 1 of t, multiply by cosine omega C of t, plus EM2 cosine omega 2 of t multiplied by cosine omega C of t. So this is mainly what you're going to implement what? Using LabVIEW. So in the spectrum, we're going to expect 5 peaks. What at omega C? 1 at omega 1 minus omega C, omega 1 plus omega C, omega 2 minus omega C, omega 1, omega 2 minus omega C. So we're going to find like 5 peaks in the spectrum. But again, the envelope will be what? Something like that, right? Again, still, you're going to have like an AM envelope. And from that, as I said, we can find out these 2 peaks, so then we can find the modulation index, or we're using the formula of M is equal square root of M1 squared plus M2 squared. Okay, is it clear? So we call this type of A modulation is double sideband full carrier. So we're sending the carrier. Why we're sending the carrier? Because we need this information at the receiver side to know the frequency. So then we can have like precise demodulation in this case. So, okay, so this means the modulation index will be if we have two more signal of with uncorrelated frequency modulation, a single carrier is calculated by this equations. Okay. Now, I think we have done this in the lab. What is the effect of changing the modulation index? Here is like m less than 1. We have like nice envelope, so we can recover our signal. So this is exactly same as what? Same as the original signal, right? Exactly same shape, right? Now, if we increase the modulation index to 1, still we'll get the same shape, right? So if here we increase the modulation greater than 1, we're not getting any more the same signal. So the shape of the envelope will be something similar to that, right? So we're not getting the original. If we compare this one with the original signal, they're what? They're not the same. They're different signal and they have more frequencies here, right? Here we're having like, the number of frequencies here will be increases. So that will mean the harmonic will be increasing. Do we ideally want M to be close? No, it's not necessary for M to be close to 1. So, the better modulation was going to be like 50%, which is going to be like 1/2, right? 1 is going to be like kind of, it's not good because it's going to be in the border. So the possibility of having overmodulation is going to be high. The chances to have overmodulation. So normally you need at least to be like 50% of modulation. Okay, so we talk about modulation index should be a number between what, 0 and 1. If the amplitude of modulated voltage is higher than the carrier, so then it's going to be greater than 1, they can cause distortion. If distortion is great enough, so then the intelligent signal become unintelligible. So we cannot able to differentiate from the intelligent signal with the carrier. So what is called overmodulation? So will distort the voice transmission. So you're gonna have like harsh, unnatural sound on the speaker. Distortion of video signal produce a scramble and inaccurate picture on the TV as well. If we're using like, for example, for sending a picture. And then we have done this last time. So what we're gonna see here, I'm not sure if I can run it here or not. So okay, you have seen this last time. This is like here you have like an RF amplifier, you have a local oscillator, we do mixers here, and then we talk here about like a AM receiver. We'll talk about it later on. But normally this is like the AM signal, and here we'll show like the percentage modulation, which is when it's increased greater than 100%, we're gonna have like we'll see like a clipping on our signal. It's not going to be like a sinusoidal anymore. We're going to see something similar to that, right? So this clipping, that means what? More harmonic will be introducing to your signal. Okay. So here we talked about, okay, again, it's like going to show you the modulation. So we're going to talk about like 3 peaks. This is the lower sideband, this is the upper sideband, and this is mainly what's going to be the carrier. But one thing interesting here, if I need to find out how much power I need to send the carrier, the power will be what? Anybody? How much power we need to send the carrier? How much power we need to send the carrier? So this is the carrier, right? EC sine 2 by FC of t, right? EC here represented what? Represented V peak, right? So the average power will be what?
We can't see your whole page there.
EC square, right? EC square over 2R, right? EC square over 2R, because this is what? This is, it's one RMS. RMS is going to be what? EC over square root of 2. Square it will become EC square over 2R, right? If we need to find out for the, this is for the carrier, okay?
Right.
If we need to find out the average power for the lower sideband and upper sideband, what we have? We have M Actually, same thing, right? Upper side and lower side. M EC over 2 cosine 2 by f of c plus f of m multiplied by t. So again, if we need to find out here the average power, P average is equal what? It's going to be M EC over 2 what? Square, right? Over, anybody? Over 2
2R.
2R, right? So then we're going to have what? We'll have M squared, right? EC squared over what? Over 8R, right? So if we compare the power required to send the upper sideband and lower sideband will have the same thing, right? So overall energy we need to have, if we need to find out the power for upper sideband and plus lower sideband, it's going to be what? M squared EC squared over 8R plus M squared EC squared over 8R, right? We just add them together. So now if we compare the power required for to send the carrier with the power required to send the message, it's huge difference, right? Why is it huge difference? Again, this is like EC squared over 8. Here we have EC squared over 2, right? And normally modulation index would be what? Would be less than 1, right? So again, this is what? This is going to be a fraction which is lower. It's going to be the average of upper sideband and lower sideband. So again, like one of disadvantages of sending the carrier, so we need a huge amount of power to send the carrier. But why we're sending that? So we can find information about the carrier frequency. Okay, is it clear? Is it clear? Okay.
Yes.
Good. So if we look at the spectrum here, this is the time domain, and I think you have seen that in the frequency domain. Again, we're not having like just sharp peak because it's like not a discrete. It's like a continuous system here. Okay, that's why we're having some values here, right? So again here, see the carrier is the highest, right? We have highest amplitude, right? And this one is going to be smaller. Again, that's why they're having what? They're having less power compared to what? Compared to the carrier. This is what, if we look at the 2-dimension here, this is like the 3 signals, right? This is in time domain, right? And here you're going to see what? You're going to see the frequency domain. So this is mainly the frequency domain with the combination of what? Of the 3 signals. And if you combine the 3 signals, you're going to get this nice envelope in this case. Okay, so sometimes we need to what? Signal frequency sine wave modulation generate what? 2 sideband complex wave voice or video modulation generate what? A range of sideband. If we have a complex wave, that's mean what? We're having like more than one frequency in the message. And this is going to be happening if we have like a voice or a video. So the modulation generate what? A range of sideband, which is, we have talked about one example. We have like 2 frequencies. It's a combination of 2 different frequencies, the message. So then we got like 4 sidebands rather than getting 2 sidebands. Okay. So then again, this is mainly the EM over 2. This is the amplitude of the upper sideband as well as the amplitude of the lower sideband, and this is like the carrier. So again, if we look at this question here, we're just changing the audio amplitude. Changing the audio amplitude will not changing mainly the carrier frequency, right? If we just change the audio here, mainly we're changing what? Adjusting the amplitude in this case. So we talked about that. We can skip that. So the good thing about AM modulation that it's required lower bandwidth, right? So B is equal, simply is equal 2 times FM, where FM is mainly the frequency of the message. So if we're talking about like voice signal, it's going to be range from like 300 to 4 kilohertz, but maybe in the practical they use something, greater than that, up to 10 kilohertz. So mainly I need like 20 kilohertz in order to send an AM signal. That's why if you look at the spectrum or the band allowed for the AM modulation just from 560 to 720 kilohertz. So within this band, you're going to expect all of the channel will be within this band. And you can find the bandwidth using what? Frequency of upper sideband minus the frequency of lower sideband. You can use this one also as well. Okay, let's look at these examples here. Standard AM broadcasting station is allowed to transmit modulation frequency up to what? 5 kilohertz. Okay. If the AM station is transmitted on a frequency of 980 kilohertz, this is the carrier. What are the sideband frequency and the total bandwidth? Okay. So what is given here is what? The FM, right? FM is equal 5, right? 5 kilohertz. And also we know the carrier is what? 980 kilohertz. So based on that, we can find out the upper sideband and the lower sideband. So then simply the upper sideband, lower sideband are going to be what? 980 plus 5, which is 985. And lower sideband, 980 minus 5, which is 975. So this is the upper sideband, it's the lower sideband. To find the bandwidth, we have two approaches here. Either we use upper sideband minus F lower sideband, which is 985 minus 975, which is equal to 10 kilohertz, or the bandwidth is equal to 2 times FM, which is 2 times 5, which is equal to 10 kilohertz. So we need 10 kilohertz in order to send this signal. Okay. Yeah, I'm gonna ask you to I'll give you like 10 minutes to this example, and then we can discuss together. So AM double sideband full carrier modulator with a carrier frequency FC is equal 100 kilohertz and a maximum modulation frequency FM of 10 kilohertz. Determine the following: lower sideband, upper sideband, upper and lower sideband. If modulation signal is a single frequency of 5 kilohertz, draw the output frequency spectrum. Yeah, would you please try to do that, and then I'll give you 5 minutes to think about it, and then we'll continue. Okay, try to do it.
Okay.
Okay, trying right now.
Good. Okay. Okay, let's go back to the questions. So we have AM double sideband full carrier modulator with the carrier frequencies given 100 kilohertz, and we have a maximum message of 10 kilohertz. So we need to determine lower sideband, upper sideband, and then the bandwidth, and then the upper lower sideband if we change the message to 5 kilohertz and then drop the spectrum. Okay, so then this is how it's going to be looks like. Let me see. Can you see it? Can you see the slide here or no?
Yes, I can see
Only
it.
see the 5 lines.
Yeah, this is the 5 line, which is going to be what? It's going to be 110, right? 90, right? And 105, and as well as what? 105 and 95. So this is mainly what you're seeing here. And as well as the carrier. The carrier is what? The carrier at 100. So then you're going to see here what? 110.
100 max in the spectrum, correct?
This is, yeah, this is 100, right?
The carrier is always bigger, correct?
Yeah, so this is 100, and this one will be what? 105,
105.
right? And this will be what? 110,
110.
110, right? And then this
Correct.
is 95, and
Yeah,
this one will be
90.
90, okay? Was it clear? So this is made of the spectrum is going to be, looks like.
I understand the spectrum, Dr. Tam, but the bandwidth, so the bandwidth will still be 10 kilohertz?
No, the bandwidth.
When the max is 5
Good
kilohertz?
question. The bandwidth would be the maximum, would be 20 kilohertz.
The maximum.
Yes, from 90 to 110. Okay, so the bandwidth would be the maximum.
From 90 to 110, why is that the bandwidth? It's just because those are the spectrums that are shown in.
Yeah,
here?
because if I'm using just only from 10 kilohertz, I can only send this signal, right?
Yes.
Right. So I need like 20 kilohertz to send the two signals, maybe. Okay.
Okay.
Mm-hmm.
I guess I was just reading the question. The question wasn't making sense. The way I read the question was, if it's draw it if it's 10, and then draw it if it's 5. Part C asked if it was 5. Maybe I just misread the question.
I read it the same way, Chris. I read it the same way, so.
I cannot. Okay, go ahead. I cannot hear you clearly. Sorry. Yes.
I hope you can hear me now. Chris, I read it the same way too. I agree. It was worded kind of strange, but when I'm looking at the solution, it makes sense. But I am wondering, Tayem, why the 5 kilohertz sidebands are taller than the 10 kilohertz.
Depend on the amplitude, you know. If the amplitude of the carrier is going to be, the message is higher, it can be, you know. So it's depend. It's not necessary.
It was not given as higher, so how would we know?
This is just, it's just like a sketch, the assumption, you know. Maybe assuming here like the one with 5 kilohertz has higher amplitude rather than the one with you know, with a 10 kilohertz. Because if you need to find the amplitude, as we said, what is the amplitude will be? The amplitude will be what? Is related to what? Related as well as to the message amplitude. Okay. So this one you can check. You can check when you do like your lab. See which one is going to be like. It's going to be like bigger. Again, yeah. The higher the amplitude is going to be like. Definitely, it's going to be bigger. Okay. But if both of them having the same amplitude, we're going to expect to have the same, you know, the same amplitude in this case. So it's just an assumption. Okay. So the height here, the amplitude depend on the amplitude of what? The amplitude of the message as well as the carrier, because it's going to be a mix of both. Okay. Now, assume if I'm sending a range of frequency from F1 to F2. I'm not sending only one frequency. I'm sending, for example, from 300 hertz up to what? Up to 3 kilohertz, for example. So then I'm not sending only one frequency. I'm sending a range of frequency, okay, to 3,400. Okay, this is hertz and this is kilohertz. So then This is like my baseband signal. Baseband signal, that's mean no modulation, okay? After we multiply with the carrier, what we're gonna expect? We're gonna expect the carrier here, right? And this is mainly will be what? My lower sideband, and this will be my upper sideband. Again, you know, every frequency was shifted by what? F1 plus FC and F2 plus FC. Same thing here, F1 minus FC plus F2 minus FC. Again, if I need to find out what is the bandwidth will be from here to here, right? You're going to take twice the highest frequency. The highest frequency here is what? F2. So we're going to expect the bandwidth to be what? 2 times what? 2 times F2. Where F2 is what? Is my highest frequency. Okay. So in this case, if we're going to look at the spectrum, anybody tell me how the spectrum is going to be looks like? We're not going to have only one peak, right? Right? We're going to have infinite number of peaks here. Why is that? Because we have infinite frequency from F1 to F2. It's not like only we're going to have like a single frequency as the normal if we're sending only one tone. But here we're sending what? A range frequency from F1 to F2. So we're going to expect like more components on the spectrum. Okay, here's an example.
But
For
I'll call
yes.
targets, but I'm not going to call a strategy.
Is what? I'm sorry. Here's an example. Assuming that the voice signal with the band of frequency from 0 to 4 kilohertz, so we have the range of frequency, is transmitted using carrier of what? 100 kilohertz. So then the modulated signal is going to be consist of what? The carrier frequency, right? And then the upper sideband and lower sideband, which is 100 minus 104, 100 to 104. And also we're going to have what? From 96 up to what? To 100. So we're going to have two bands here, from 100 to 104, and then from 96 to 100, and the carrier will be at what? At 100. And the bandwidth will be what? 104 minus 96, which is going to be 8 kilohertz, which is twice mainly the highest frequency, which is 4 times 2 will get what? We'll get 8 kilohertz in this case. Okay, so let's do that, and then I'll give you some time to do these questions. Okay, and then we'll continue. I'll give you 7 minutes to do that, and then we'll discuss together. So what is given here? Given the first input to the modulator is 500 kilohertz, and the carrier signal with an amplitude of what? 20 volt. Okay, this is V peak. The second input to a modulator is what? Is a 10 kilohertz modulated signal with plus or minus 7.5 V peak. Determine the following: upper sideband, lower sideband, modulation index and percentage of modulation, peak amplitude of modulation carrier, and upper and lower sideband frequency voltage, maximum and minimum amplitude of the envelope, Vmax and Vminimum. Draw output in frequency domain as well as the time domain. Okay, I'll give you like 7 minutes to do that, and then we'll continue. Okay. Okay, let's do it together, okay? So, again, first thing we need to find out what is the upper side band and lower side frequency. So we know what is the carrier and we know the frequency of the message. So simply for A, if for upper side band, it's going to be what? Side band is going to be 500 plus 10, which is going to be 510 kilohertz, okay? So I'm expecting everybody know that, right? And if lower side band, it's going to be 500, right? Minus 10, which is going to be 490 kilohertz. So the upper side band is 510, and the lower side band is 490. B, we need to find out what? Find the modulation index and the percentage modulation. We know that the modulation index is equal to the amplitude of the message divided by the amplitude of the carrier. In this case, the amplitude of the message is given, which is 7.5, right? Divide by the amplitude of the carrier, which is 20. If you do that, you will get what? 0.375. This is the modulation index. If I need to find the modulation percentage, simply we multiply 0.375 times that, times 100. So then we're going to get what? 37.5% of modulation, which is good, right? It's less than 100. And then we need to find out what is the peak amplitude of the modulation carrier and the upper side band and lower side band. So the amplitude of the carrier simply is going to be what? EC, which is going to be 20 volt peak to peak, right? 20 volt peak, right? Then we can find out the upper side band and lower side band. So then E lower side band or E upper side band simply is going to be equal to what? EM divided by 2, right? Which is going to be 7.5 divided by 2. So then it will be equal to 375 volt. Okay. So this is what's exactly determine how much the amplitude will be of the upper side band and the lower side band. You have any questions so far? Is okay? Everybody's okay?
Nope. Yep.
Okay. So now we need to find out what? Peak amplitude of the modulated carrier and upper side band. We can find it in another way here. It's exactly the same. So we know the modulation index M is equal what? Equal EM over EC, right? So from here we can find that EM is equal what? M times EC, right? So then from that we can find, we know that E lower side band is equal what? E upper side band, they're same, which is equal MEC over 2. Okay, go back to the derivation of AM signal, which is equal 0.375 modulation index multiplied by 20, the carrier divided by 2. If you do that, you will get again 3.75 peak. Or we can use just only EM over 2 to find out E lower side band and E upper side band, which is mainly the same. The last thing we need to find out what is the maximum and the minimum amplitude. Maximum and minimum amplitude can be found using we know what is EC and we know what is EM, right? So Vmax, we need this one to draw the envelope, right? Simply EC plus EM, which is going to be 20 plus 7.5, which is going to be 27.5 volt. V minimum is going to be what? EC minus EM. It's going to be 20 minus 7.5, which is equal 12.5. Okay. So we cannot find the modulation index simply by dividing Vm by Vmax, right? It is 1/2 Vmax plus Vm divided by Vmax minus Vm. Okay. Is it clear? So the last thing, we need to look at the spectrum. So this will be the spectrum. This is the lower sideband, and this is the upper sideband, and the carrier. The amplitude is 3.575. We just calculated. It's going to be same for our lower sideband, and for the carrier will be what? Will be 24. That's why it's a huge power we need in order to send the carrier. It's like one of the disadvantage of double sideband full carrier AM modulation. Now this is how it looks like, the envelope. This is the maximum voltage and this is the minimum voltage. Still, we have really good modulation because the modulation percentage is 37.5, which is really good. Okay. If we look at the spectrum, this is how the spectrum is going to be. We just look at the spectrum. So, but now the next step, I want to go through it now. So I'll give you time just to work in your lab. So we're going to talk about how much power is required, the total power we need to send an AM signal. And we'll find out like 2/3 of power is going to be consumed in sending the carrier, which is going to be like wasting. But we need that if we're looking for really to get the high accuracy of AM modulation. Okay? Was it clear?
Clear.
So now let's summarize what you have to do for the lab. Okay? What you have to do for the lab, you have to, using LabVIEW, you're going to implement AM modulation using what? Using one message, and then try to calculate the modulation index from the graph, from the time domain. And in the next step, you need to combine two messages with different frequency and multiply with the carrier. And again, see, you have to look at the spectrum. And you have to compare the modulation index from the graph, from the time domain, with the formula that what we discussed. M is equal square root M1 square plus M2 square if you have two messages. Okay, it's clear?
No, that was a lot of information really fast. How are we supposed to, do you have like a document we can look at with a lab manual, or can you please write down what we're supposed to do?
Okay, I will write it down and I will post it in D2L. Okay, but if you need to work on it right now, we just need to do what? We just need to do like the message multiply with the carrier. If I go back here, let's see. I'll show you what you need to do. Okay. This is my AM signal, right? This is my AM amplitude modulation signal, right? So we're having the carrier here, plus what? The message multiplied with the carrier. You need to implement this one in LabVIEW, okay? And you have to assume what is the amplitude of the message and what is the amplitude of the carrier. Implement this one in LabVIEW, in time domain and frequency domain. Is this clear?
So you just want us to add a couple of sinusoids or something?
Yes, but you have to here to change the modulation index and find out to play with the amplitude of the message, amplitude of the carrier, and look at the spectrum, how it's going to be changed, as well as to the time domain as well.
Okay, so the first bullet point is just to implement that one equation,
right,
and output it to a filter or something. What are we?
You have to see that the frequency domain and the time domain. You need to be filtered. Just start to like the FFT, the spectrum, as well as the time domain. Just display the time domain and the frequency domain. Okay. Yeah. So in your display, you're gonna come up like with a good, really like interface where you can change the voltage of the carrier, the voltage of the message. You don't take like only one fixed value. The frequency of the carrier, the frequency of the message. So try to use not fixed controller. That's what I'm saying here. Okay. Use a variable controller, so you can't control the amplitude of the.
So put a slider for all the different variables.
Yes. It's gonna be like you have like multiple. You gotta try multiple voltage, multiple frequency. Okay, and then you're gonna study like under modulation, over modulation, as well as and look at the spectrum. What's gonna happen for the spectrum? Okay, this is like the first part. The second part, rather having only one message, you're gonna add another message here. Okay, so you're gonna have like Vm1 of t times cosine omega c of t plus you're gonna add another message here, Vm of 2, okay, another frequency, multiply by what? Cosine omega c of t. Okay. So here you're having what? You're having two messages here. Again, you need to implement this one in LabVIEW and look at the spectrum. You can have like five spectrums here, 5 peaks in the spectrum, which is the carrier, and upper sideband, lower sideband for this frequency, and upper sideband, lower sideband for the frequency of VM2. Okay. And from the envelope detector, you can find out the Vmax and Vminimum. So then you can find the modulation index. And use theoretically the modulation index, which is M is equal square root of what? M1 square plus M2 square. How you can calculate M1 square plus M2 square? If you know what is the amplitude of each message, V1, VM1 of t and VM of t, and you know the amplitude of the carrier, then you can find out what the modulation index. This is one way, right? The other way is from the envelope detector. You can look at the envelope detector after you implement the LabVIEW and look at your envelope detector. From the envelope detector, I can get what's this value, which is Vmax, right? And which is going to be what? EC plus EM, and this would be my Vminimum. From Vmax and Vminimum, we can use the formula that's on the slide, and then we can calculate the modulation index here. And then we compare the modulation index here from the graph with the modulation index from the formula here. Is it clear?
Yes.
Is it clear
Yeah.
now?
So it's
Is
just
what?
two sections. Just two sections. One of them, we're just implementing one message and modulated. And then in the second part, you want us to add
messages.
another sinusoid
Yes.
before we modulate.
That's true. Yep.
And then you're saying we should be able to use the same procedure to find the
Yes.
Vmax and Vmin even with two sinusoids, because it won't look sinusoidal anymore. So how do we know what the real peaks and stuff is?
It's gonna be like sinusoid still. It's gonna be sinusoidal again. It's still gonna be the envelope, even if you have
only if they're the same frequency.
Yeah, but still
different frequencies that have like a different kind of waviness to it.
It's gonna be different. It's gonna be something like this, but see, it's not gonna be exactly like smooth, right? Because the combination of two signals. But still, you can find the peak and you can find out what is the minimum. Okay, just compare, find out. Match will not be that match, but find out if this is match or not. You know, so just like find out.
Okay, we'll investigate that.
Okay, yeah, just investigate and find out and just put your conclusion. Mikey will say, yes, it's not a procedure, it's not good. You cannot find out from the time domain the modulation index. We have to use this formula to find out what would be the modulation index. Okay? Is it clear?
Clear.
Okay, and I will write up and I will post it in the Blackboard by detail by tomorrow if for somebody is not clear to what exactly you need to do. Okay? And hopefully we'll able to get remote access to the Elvis will make our life easier, but let's see. Tomorrow I will be in the school. So Sirjan, you will be in the school tomorrow, right? Which time will be in the school?
Yes, sir. Well,
which time?
I'll go there at 9.
9 o'clock. Okay. So I might be there by 10 o'clock. Okay.
Sounds good.
So I'll see you then. You're safe? You're good?
I'm good. Yes, sir.
Okay. No, I'm just kidding. Okay. We'll see you tomorrow. Then, yeah, please try to do that. And if you have any question anyway, you can text me and then I will, or you call me, you know, then we can go through that. Okay.
Yes, sir.
The question
yes.
of this lab. So I have no idea what lab number this would be and what to call, like what we're doing today. So this is modulating complex signals?
Yeah, just amplitude, you know, amplitude modulation. You can just amplitude
We've already had a couple called amplitude modulation, though.
Yeah, amplitude modulation, the other one we did in hardware, right? This is like using LabVIEW. You can name it.
Okay.
Amplitude modulation using LabVIEW software. Okay? Okay, then we'll stop by here and we'll see you next week, okay?
Okay.
Thank you. Thank you.